Welcome to the next installment in the Kenexis webinar series, this session entitled Performance-Based Fire and Gas System Engineering. I am the speaker today. My name is Ed Marszal. I am the President and CEO of Kenexis. I have been involved in safety instrumented system engineering and all instrumented safeguard engineering for over 20 years now. I am the author of the ISA book on safety integrity level selection, entitled Systematic Safety Integrity Level Selection with Layer Protection Analysis. I'm also very active on ISA committees related to safety instrumentation, including S84, the former S91, which is now a working group of S84, S18 for alarm management, and the S84 work group 7 that's involved in fire and gas detection and suppression system design. I'm also a past director of the ISA Safety Division and very active in the Safety Division. A few years ago, I was elected as an ISA Fellow, a member of AICHE, NSPA, and various other organizations that are involved in the design of safety critical instrumentation, and originally received a bachelor's degree in chemical engineering from the Ohio State University. And I would also like to highlight that I am an ISA 84 expert. That is a certification designation for expertise in all facets of safety instrumented system design that is provided by ISA. The ISA certification is something that we at Kenexis highly encourage, as it is the only really truly independent certification from a standards body that is a third-party nonprofit organization completely uncontrolled by any commercial interests. Okay, and a little bit about Kenexis. Kenexis is a consulting company that is involved in the design of instrumented safeguards. And our expertise in the ability to perform engineered instrumented safeguard design comes from the fact that the company is built on 3 factors, whereas other organizations are only built on 1. Kenexis has a foundation in control system engineering, so we understand how to apply, how to design at a very fundamental level the instrumented safeguards that we are specifying. We also have an incredibly high degree of expertise in risk analysis. Detailed quantitative risk analysis including detailed dispersion and explosion modeling, fault tree analysis, Markov analysis, event tree analysis, and various other risk analysis techniques. And on top of that, most of the engineers at Kenexis are chemical engineers, so we have a very high degree of knowledge in process engineering. So we understand the process itself, how to analyze the risk of the process, and then finally how to actually implement the design to perform the risk reduction. And Kenexis is unique in being able to field a team that has all of that expertise in-house. Okay, all safety instrumentation needs a basis of safety, including fire and gas systems, FGS, fire and gas detection and suppression systems. And what we mean by a basis of safety is that some sort of standard or some sort of procedure, some sort of process needs to be available to ensure that the adequate equipment is selected and designed for the process that is under control, that is under study. So some sort of process needs to be available to make sure that if a fire and gas detection and suppression system is required, it will be implemented. The design will provide the appropriate amount of detectors, that those detectors will be in the correct location, and that the proper technology will be selected. In addition, the basis of safety is going to need to specify the mechanical integrity requirements, meaning what type of preventive maintenance tasks are going to be performed on the equipment, at what frequency are those tasks going to be performed. So some sort of basis needs to be provided to make those decisions for the equipment selection and the mechanical integrity program definition. Traditionally, for fire and gas systems, there have been two ways that the basis of safety has been defined. The more traditional method is a prescriptive basis of safety. And by prescriptive, we mean that there are standards, such as those standards from the National Fire Protection Association, NFPA, and also European norms that will define what type of equipment you need to install, where you need to install it, and how you need to maintain it. Some of the more common standards would be the National Fire Alarm Code, NFPA 72, and also the equivalent standard in Europe would be European norm EN 54. Now that is the more traditional method, and there have been problems in using these prescriptive methods in that they don't allow for the optimal design for all situations, especially open air process plants and offshore oil and gas production facilities being a perfect example of where some of these prescriptive standards fall short of providing a good basis of safety. As a result, newer techniques have been used to try to create more optimal designs, and the basic description of the new methods are performance-based methods that use risk assessment to make the decisions as to where equipment is required and how often it would need to be tested. Okay, as I mentioned previously, some of the prescriptive standards for fire and gas design include items from the National Fire Protection Association, and those standards provide a very comprehensive set of rules for designing equipment. These methodologies and standards are very well established for the design of detection and mitigation systems. And they do provide a lot of detailed requirements for many types of fire and gas systems. But they do not provide the detailed requirements that are going to be required in chemical processing areas. Most of the fire alarm code and all of the other associated standards are really built around the protection of occupied buildings, such as office buildings, hospitals, schools. And they're not geared toward the very specialized requirements of processing flammable materials and processing toxic materials. Toxics are completely unaddressed by these codes. But what these standards do realize is that they cannot provide a comprehensive set of rules for every situation. So many of these standards allow for the use of performance-based alternatives where the results that are provided by the prescriptive standards just do not provide the results that are required to adequately safeguard a facility. Again, these methods and these standards in the prescriptive standards are generally not specific to chemical processing. As a result, more tools and more techniques that specifically address chemical processing needed to be developed. Okay, into the gap of the performance-based standards and the process industry applications for fire and gas detection equipment, this is in this area is where a lot of the practitioners in industry decided that more guidance was going to be required. Specifically, the International Society for Automation, ISA, developed a working group under the S84 standards panel specifically to address fire and gas system design. The Working Group 7 created a technical report, report 84.00.07, and the purpose of this technical report was to provide guidance for fire and gas systems and how they can be designed in accordance with the principles of the ISA 84/IEC 61511 standard. And again, the IEC 61511 standard is the general international standard for safety instrumented systems, whereas the ISA 84 is the U.S. specific version of the IEC 61511 standard, which is essentially identical, other than a few additional sentences. Now, the reason that the IEC 61511 standard was chosen as the basis for future FGS design was that the 61511 standard has been implemented in various forms since 1996, when it was originally issued as the ISA 84 standard. The IEC 61511 standard followed a few years later in 2000. And there has been a lot of widespread acceptance of this standard and a lot of successful implementation for safety instrumentation in general. As a result, a lot of operating companies and a lot of engineering companies strongly desired to use the performance-based rules and techniques in the IEC 61511 standards to design not only their emergency shutdown systems, the traditional SIS, but also fire and gas detection and suppression systems and a variety of other safety instrumentation. In general, the way the IEC 61511 standard works is that performance targets are specified for each safety instrumented function or a control loop that performs a safety purpose. And that target is selected based on the risk associated with the hazard that the safety instrumented function is intended to prevent. Well, while this approach works very well for safety instrumented systems, it falls a little bit short for fire and gas detection and suppression systems because FGS systems in general do not prevent a hazard, they mitigate a hazard, making the consequence smaller instead of preventing it altogether. As a result of that subtlety of the difference between preventive and mitigative systems, a lot of additional engineering and a lot of additional specification needs to be performed in order to fill the gaps. But in essence, what the ISA 84 Working Group 7 came up with in a technical report is that a fire and gas system can be designed quite similarly to an SIS if an additional consideration is made during the design. So instead of just assigning a SIL target or a safety availability to the loop, it is also important for a fire and gas system to specify the detector coverage. So the determination and quantification, verification, and validation of the detector coverage is going to be required when using a performance-based fire and gas system design, in addition to looking at the SIL target or specifically the safety availability target. Now, this standard was specifically written for the process industries and was not intended to be all-encompassing going back to your typical occupied buildings. So again, we're only going to be looking at the process areas of a facility when we start using the technical report as a basis for the fire and gas system design. And the other thing to note is that this technical report is not intended to be a replacement for the prescriptive design. The prescriptive design techniques are still going to apply to a lot of areas of a facility. So if you were looking at a typical refinery, you would still want to design the fire and gas systems in the control rooms, in motor control centers and other occupied buildings using the requirements in NFPA 72. It is not a replacement. It is only a supplement for things like toxic gas detection and fire and gas detection in outdoor areas. So one would often ask, well, which approach should I use? Should I use the performance-based approach, where I simply analyze the risk and apply as much instrumented safeguards as are required to mitigate that risk? Or do I follow a completely prescriptive approach where I just follow a rule set and check off the numbers as they are completed? Well, in reality, it's best to use a combination of both prescriptive and performance-based methods. Many of the fire and gas system elements are going to be adequately addressed by the prescriptive standards. And using prescriptive standards is going to give you a very rigorous design, and it's going to be very effective and very quick, whereas the performance-based standards are going to be a lot more time-consuming, require a lot more analysis. So if some of the fire and gas system elements can be addressed using prescriptive standards, that is the quicker and more effective way to go. But a lot of the methods a lot of the elements that, even though they are addressed by prescriptive standards, could be better designed using performance-based methods. It will allow for better detector placements, more effective determination of quantities and locations. And some FGS elements that are often found in the chemical process industries are not covered by prescriptive standards at all. So things like placement of toxic gas detectors in open areas is something that is not addressed at all by any standards that are currently available. So using using performance-based techniques to address these standards is really the only feasible option. Now, the ISA 84 Technical Report 84.00.07 has defined a life cycle for the application of fire and gas systems. This life cycle is very similar in nature to the safety instrumented systems life cycle in the IEC 61511/ISA 84 standard, but adds a few more issues that are directly related to the fire and gas systems. So the life cycle that's defined in ISA 84TR.84.00.07 starts with identifying areas of concern. You don't want to apply fire and gas systems across the board to every facility. You want to consider the equipment that you're analyzing or the equipment that you have in your facility to determine whether there are any fire and gas detection and suppression concerns. If there are concerns, you're going to want to identify the risk scenarios, which will define what type of detection and suppression equipment you would need. For each of those scenarios, you're going to want to analyze what types of consequences can occur as the result of those hazardous events, and what the overall impact on the people and the facility if those consequences were to occur. In addition to the magnitude of the consequence, you're also going to want to be concerned with the frequency of the consequence. The more frequently a fire or a gas release will occur, the more rigorous and more effective the countermeasures or the risk mitigation system will need to be. Considering all of that information, you'll perform an unmitigated risk assessment, determining what the risk is with the situation as it is before the fire and gas system is applied. If that risk is acceptable, then no system will be required and you can stop at that point in the safety life cycle. But if the unmitigated risk is not tolerable, then you'll need to proceed on to the next step of the safety life cycle, which is identifying fire and gas system risk reduction requirements. So you'll determine what type of fire and gas system equipment you're going to need. Next, you'll need to develop an initial design. For fire and gas systems, we don't recommend trying to set a target out of thin air. You're going to want to use your heuristics from experienced fire and gas systems engineers to provide an initial design, an initial layout based on the type of equipment, the type of facility and how the various pieces of process equipment and support equipment are laid out. All of the initial design is performed using heuristics or rules of thumb. But the difference between the previous way of designing fire and gas systems and what is espoused in the ISA 84TR.00.07 technical report is that we don't stop using rules of thumb. After the initial design has been laid out, the detector coverage is calculated. So the effectiveness in terms of how much coverage a fire and gas detector array can achieve is specifically calculated instead of simply looking at the rules of thumb and using that as the final arbiter on where equipment should be placed. In addition to the coverage, we'll also calculate the safety availability of the fire and gas equipment. The electrical equipment that is in the control loop will be calculated, the safety availability will be calculated in the same way that a SIL would be calculated for a safety instrumented function in accordance with the IEC 61511 standard. After that, we'll be able to perform a mitigated risk assessment. So now we originally looked at the risk without the benefit of a fire and gas detection and suppression system. Subsequently, we will look at the risk after the mitigation has been put in place. If the mitigated risk is acceptable, then we leave the initial fire and gas system design as being validated and move on to the next zone or the next system. If it does not achieve the requirements, then we'll analyze the areas where the design failed, propose a new design, and then go back to step 8 where we assess the coverage and continue in a loopwise fashion until the proposed fire and gas system meets the requirements of the tolerable risk. Okay. Now, the ISA 84 technical report is going to be consistent with the underlying principles of the IEC 61511 standard and also the ISA 84.00.01 standard, which is essentially the same. Now, this process does not provide a complete guidance process. It doesn't provide a complete process for fire and gas system design. It is only intended for application to process areas. Areas of occupied buildings are still going to need to conform with the prescriptive standards that are applicable in that jurisdiction, such as NFPA 72, if your facility is going to be located in the United States. Now, what was shown to you previously was the safety life cycle as presented in the TR 84.00.07 technical report. And the way that life cycles are written in the technical reports and in the standards is really more of a placeholder for the requirements for the various sections and phases of design. And those safety life cycles should never be used as a flow chart for how to actually execute a project, because that was never their intention. The intention of those life cycles is a structure for listing requirements as opposed to a procedure for executing a project. What I'm presenting in this slide is more of a procedure for executing a project or a typical workflow for a performance-based fire and gas system design. In the typical workflow, you'll begin with a requirement for fire and gas system design. So coming into this flow chart, there will have been some sort of trigger that would require an engineering team or process design team to consider the need for fire and gas system design. This might be as the result of regulatory requirements. This might be as the result of design procedures from an operating company or an engineering company. It might be the result of a process hazards analysis or a PHA HAZOP perhaps recommendation. Or it could even be something like the recommendation of an insurance auditor or a regulatory body audit. If for whatever reason there has been a request to analyze the design of the fire and gas detection and suppression systems, you'll start into this workflow. The first piece of the workflow really should happen prior to execution of the workflow and should only occur one time and then be revalidated and have multiple projects execute under it. And that's going to be the development of the overall fire and gas system philosophy. This is going to be the creation of a set of documents that defines the tools, the techniques, the policies, and the procedures surrounding fire and gas system design. There are a lot of options that are available to you that all comply with the IEC 61511 and standard and the ISA 84.00.07 technical report. And it is the purpose of the FGS philosophy document to select the specific tools, techniques, philosophies, policies, and procedures that will be employed at a given facility to ensure that you're going to have consistent design from plant to plant and facility to facility within the same organization. After the fire and gas system philosophy has been developed, the next step in the recommended approach is to define the zones. Fire and gas systems are going to be broken into small areas or zones that are geographically limited and also narrow down and define the specific actions that need to be taken and hazards that are present within a certain area. Zone definition is going to help in determining how systems are laid out, and they even go as far as to help first responders and other people that are responding to fire and gas situations to determine where the hazards exist and how to best address the hazards that have been realized. After all of the zones have been defined, we need to determine the performance requirements for that zone. So for each zone, we're going to set various requirements such as the safety availability of any FGS functions that have been defined for that zone. And also we're going to set the coverage requirements for the fire and gas detection arrays that are covering that zone. After the performance targets have been specified, we are going to verify that the requirements have been achieved. We will first verify the coverage using quantitative models to calculate the coverage that has been actually achieved in a zone and compare that against the target. And then we will use the traditional SIL verification techniques to calculate the fire and gas system availability. And these are the same techniques that are being used for IEC 61511, and the best source for the techniques and tools for fire and gas system availability calculation would be the ISA technical report on SIL verification, technical report TR 84.00.02. Now, if either the detector coverage targets or the safety availability targets are not achieved, then we will go back and modify the initial fire and gas system design as specified by a fire and gas system expert using their heuristics for placement. Then you're going to need to go back and change the design, looking at the coverage maps and looking at the availability calculations to determine where the weak points are and rearranging your detector placements and other attributes such as redundancy and test intervals and even the type of equipment that you're employing in order to improve your coverage or availability, whichever did not achieve the target design, and then rerun your verification calculations. And this process, again, is going to occur recursively until the performance targets have been achieved. After the performance targets have been achieved, the next step is to specify the design of the fire and gas system that has had its coverage and availability defined. And this is akin to the safety requirement specifications for a traditional safety instrumented system. As a matter of fact, many people will refer to these specifications as the FGS safety requirement specifications. This is typically going to include things like detector placement drawings, cause and effect diagrams for the actions that are taken by the fire and gas system, and also general requirements on the attributes for performance of the fire and gas system. After the design has been specified, procedures need to be developed for maintaining and operating the system. So operations procedures for how to interact with the fire and gas system in normal situations and also emergency situations, and also procedures for maintenance of the system, including testing procedures and other preventive maintenance tasks. After the design has been completed, the construction, installation, and commissioning phase occurs, where the equipment is installed in accordance with the FGS safety requirement specifications. After installation and commissioning has occurred, there is a validation step, or sometimes it's referred to as the pre-startup acceptance testing phase. This is where all of the functionality of the fire and gas system will be verified in terms of looking at the actual equipment, where it was installed, how it was installed, and how it was programmed to verify that the design meets the requirements of the fire and gas SRS, and also actual physical testing of the system to ensure that its performance matches what was specified in the fire and gas system SRS. After the PSAT, the system is turned over to operations and maintenance for day-to-day operation. And day-to-day operation will include simple things such as responding to alarms, responding to failure alarms, and then periodic function testing and preventive maintenance tasks to ensure that the performance levels that were specified will be achieved through the life cycle of the facility. And finally, we have listed a management of change step. Essentially, any change that occurs to the facility or to the fire and gas system itself needs to be considered, and it needs to drive the design back to the appropriate phase in this typical workflow or the safety life cycle to ensure that as changes are made, the required performance of the system still matches, the requirements of the system and the actual design will match. Okay, going through each one of these steps in a little bit more detail in order to provide a more sound basis for what occurs during the various phases of the the FGS safety life cycle. Again, the first step in the FGS safety life cycle is the identification of the need to perform a fire and gas system design. There are a lot of studies, a lot of formal process hazards analyses that will result in the recommendation to implement or possibly the recommendation to set targets for the fire and gas system design. These studies would include things like process hazards analysis, typically done using something like a hazards and operability study or a HAZOP, or checklists or what-if studies. there are many situations where the scenarios that are being considered under these process hazards analysis techniques will result in the study team being concerned that the existing risk profile is unacceptable and then making a recommendation for the implementation or at least the study of the use of fire and gas detection and suppression systems. Also, other more detailed risk analysis techniques such as layer of protection analysis often recommend that fire and gas system designs be considered. And finally, a lot of jurisdictions require the use of quantitative risk assessment studies as part of the licensing or the license to operate phase of a process design. And in a lot of cases, a quantitative risk assessment study may actually assume that a fire and gas system is in place and is in operation when they analyze their risks. So if a quantitative risk analysis has been performed for your facility and it was the basis to go to a regulator to get an operational permit, then the actual facility needs to have a fire and gas system in place that whose performance is in accordance with the assumptions that were made during that quantitative risk assessment study. In a lot of cases, fire and gas system implementation is going to be required by government regulation. A lot of regulators will specifically stipulate that if you want to operate a certain type of facility, such as perhaps a liquefied petroleum gas storage facility, they're going to require that you implement some degree of fire and gas detection and suppression systems. Also, there are industry standards and corporate standards that stipulate that if you are going to operate a certain type of facility or certain types of process equipment, that equipment or those facilities need to have fire and gas detection and suppression systems incorporated as part of their design. And finally, in some cases, insurance providers, as they audit your facility, will be checking to see what degree of fire and gas systems are installed, and if the insurance assessor determines that your fire and gas system is inadequate or inexistent, they may recommend that you implement such a system, with a penalty for not implementing ranging from increased premiums to outright refusal to underwrite your insurance policy altogether. Okay, the next stage in the fire and gas system life cycle is the development of the fire and gas system philosophy. And as was stated previously, the development of a fire and gas system philosophy is not something that should be recurring every time a fire and gas system project is implemented. This is something that should be done once at the site level or possibly at the corporate level, and then applied consistently to all equipment, all processes, and all facilities in an organization. Now, the development of a fire and gas system philosophy is going to include multiple elements. First off, the fire and gas system philosophy is going to standardize the methods that are going to be used for categorizing the hazards that fire and gas systems protect against and the risk associated with those systems. First, there's going to be criteria for hazard identification. So for instance, for process facility areas, or process facility equipment, there will be rules established to determine whether or not a zone or a piece of equipment has any hazards associated with it. And these criteria might include things like what type of material is being contained in the process equipment with respect to whether or not it's flammable. If it is flammable, information about the nature of the potentially released material, such as its molecular weight, and also the processing conditions, such as the temperature at which the material is being processed, and also the pressure, which will drive the risk. So those are the types of criteria that will determine whether or not an equipment item or an area is even considered for fire and gas system mitigation. If areas are going to be considered for fire and gas system mitigation, then criteria is going to be required to categorize the degree of risk that equipment presents. So some equipment, such as high pressure compressors, are going to pose a much higher risk and thus require much more mitigation than lower risk systems such as methanol storage tanks for methanol injection. And finally, the philosophy is also going to have to list the requirements for what safety analysis is going to be performed. How are those analyses going to be broken down into the various risk studies, and what are the procedures by which those studies will be carried out? Now, in addition to setting up the methods and procedures by which the FGS system is going to be analyzed and designed, there will also be various heuristics or rules of thumb that are going to be used internal to those procedures. For instance, there will be criteria for how to define zones, what the extent of those zones are going to be, and how you may want to grade those zones into different risk categories, which will have different associated performance targets with them. There will be criteria for assigning performance targets to various fire and gas system equipment. There is going to be criteria for selecting which type of technology is going to be appropriate for the various types of sensors that are available for detecting fires and detecting gas releases. So, for instance, rules of thumb for when to use frangible bulbs or bimetallic heat detectors as opposed to optical fire detection equipment. There will be rules of thumb for how things are alarmed, when they are alarmed, and what those alarms look like in terms of audible enunciation and visible signaling. There will be rules of thumb for when manual activation is required and where those manual activation systems or manual alarm call points, MACs, will be installed. There will be rules for how to vote various detection equipment, possibly in hopes of reducing nuisance alarms. And then there will also be criteria for selecting which set points are going to be used to activate alarms and to activate control actions based on fire and gas system detection. All of this information needs to be defined prior to going into the detailed implementation of any project. And again, this should be done at a higher level in the organization and then consistently applied across all equipment in all facilities. Some of the procedures that are going to result from the development of an FGS philosophy will include a hazard identification procedure, which is going to allow you to determine whether or not hazards are present, and if so, what type of hazards are present. Then there's going to be a procedure for defining zones and setting grades and extents of the grades for those zones. Then you'll have another procedure for establishing performance targets or setting performance targets for the equipment. And finally, you will have rules, procedures, and probably even standardized tools for assessing that the performance targets have been achieved. So tools for verification of the performance targets of safety, availability, and detector coverage. The next step in the workflow for the design of fire and gas systems is going to be the definition of zones. Before starting out in the zone definition process, you're going to want to have a full understanding of the process that you're analyzing. This would include things like having process flow diagrams, piping and instrumentation diagrams, cause and effect diagrams for the fire and gas system if they have already been available at this preliminary stage or possibly for an existing facility. And most importantly, you're going to want a plot plan or a deck plan that physically shows where equipment is located in relation to the facility as a whole and with respect to other equipment. You're then going to want to use some sort of FGS design toolkit to develop the fire and gas zone list, which is going to be the output of this task. Okay, in terms of why fire and gas zone definition is so important, different areas in a processing plant have different fire and gas hazards. There may be building zones where the goal is to protect the personnel and the assets in that room or in that zone from general building fire hazards. You're going to have completely different hazards in processing areas. And even within those processing areas, some areas may have toxic hazards where other areas do not. Some areas may be prone to pool fires where other areas may be prone to gas releases or gas jet fires. So understanding what hazards are present through the hazard process is going to help us to define what the zones are, segregate the zones for each other, and then set the performance targets internal to those zones. Also, there is a special type of zone where you're trying to segregate a process area from a non-process area. This would include things like air intakes into control rooms, motor control centers, and also airlock doorways that separate a process area from a control room. And the intention of these zones is to prevent the potential hazards of combustible and toxic materials from leaving the process area and entering a non-process area where they can either impact humans or be ignited by unrated electrical equipment inside a non-process area. Also, the definition of the zones is going to allow you to clearly communicate what hazards are present and where those hazards are located when a release occurs or a fire occurs. And it's going to be important to transmit this information to your operations staff so they can take process actions to mitigate the hazard. And also it's going to be very important for emergency responders so they know what actions they're going to need to take and where those hazards are located so they can develop an effective strategy for going in and taking emergency response actions. Now, once all of the zones have been defined geographically, you're going to want to categorize them, and the categorization of those zones is then going to help you to select the mitigation techniques that are going to be employed for that specific zone. The categories of the zone that are typically used in performance-based fire and gas design are shown in the table below. The zone categories range from the zone categories are H, N, G, E, T, Z, which all define different attributes of a process zone. The first type of zone is type H, and that is a hydrocarbon processing area. This is an area where the process facility is processing hydrocarbons, and as a result of that processing, there can be leaks, which may result in a fire hazard or a combustible gas hazard. Also, if toxics are being processed in that area, it could result in a toxic gas hazard. And some examples of this type of zone would include a production separation area or a gas compression module. The next type of zone is type N. Now, these are still process areas, and these process areas still contain fire hazards, but they may be non-hydrocarbon fire hazards. And this could include things like combustible liquid storage, such as methanol storage tanks, or possibly lubricating oil systems. The reason that these zones need to be separated from the traditional hydrocarbon processing areas is that the sensors that are used to detect these fires may be different from those that would be used in the traditional processing areas. And also, the countermeasures that are used in these zones may be different from the traditional process areas. The next type of zone is a G zone. This would be general occupancy, where there's no hydrocarbon fire hazard. And this would include things like accommodations areas of oil and gas platforms, control rooms of any typical process facility, workshops, other areas that are normally occupied by people, but where chemical processing does not occur. E, the next type of zone, is a non-hydrocarbon special equipment protection. And typically what we're talking about with a type E zone is a zone where we are concerned about separation of hydrocarbon area from a non-hydrocarbon area, specifically because the zone contains unrated electrical equipment. So this would include things like motor control centers or instrumentation and control rack rooms, where if hydrocarbon were to ingress into that area, it could find a source of ignition and cause an explosion. The next type of category is a T, which is dedicated to gas turbine enclosures or engine enclosures. These types of areas have very specific and in some cases very prescriptive requirements for the type of fire and gas equipment that are going to be required. Finally, there is a type V, which is dedicated to air intakes or ventilation. So ventilation air intakes into occupied facilities, and also combustion air intakes. And again, like E-type zones, V-type zones were primarily concerned with segregating the hazards of the process area of flammable or toxic gases and preventing those hazards from migrating into another area through an intake system. The result of the fire and gas zone definition is going to be an FGS zone list, as you can see in the example below. The complete list of FGS zones for a facility will be created during this task, and for each item, you're going to identify what the zone is, typically some sort of tag number that defines the zone. You will describe the zone to give a little bit more verbal description and context for where the zone is located and what the zone contains. Next, you will define the category for the zone along with some of the attributes that caused you to select that zone type for the zone under study. After the FGS zone list is completed, The next step in the performance-based FGS design is going to be to determine the FGS performance requirements. And the FGS performance requirements is going to be performed using the FGS zone list to tell you which zones you need to set a performance requirement for, and also the procedures coming from the FGS philosophy that will set procedures, requirements, and also tables and tools for selecting what the performance requirements should be. Again, we would recommend that you use some type of automated database toolkit to perform this task with the philosophy rules built into the database. And the ultimate result will be a fire and gas system design basis report and performance requirement selection worksheet tables specifically. Now, when you're selecting performance targets for a fire and gas system, you are essentially doing a risk analysis. You are analyzing the risk that the fire and gas hazards present inside a specific zone, and then you're going to set performance targets that are hopefully going to reduce that risk to a tolerable level. So when we're performing this risk analysis, we're going to essentially need to develop some sort of model that defines what the risk is and what level of performance is required to make that risk tolerable. When we are setting up this risk assessment model, we're going to want to ensure that the model is going to be sensitive to both the coverage that the fire and gas detector arrays can provide, and also we're going to want to make sure that it's sensitive to the probability of failure on demand, which is associated with the SIL of the fire and gas loops that are going to be performing the functionality. In addition, the modeling technique is going to need to include a lot of the considerations that define the risk, such as what type of equipment is going to be contained in the zone. And that type of equipment is also going to consider, well, what is the material that is being processed by the equipment? What are the temperatures and pressures that material is being processed under? All of that is then going to drive what are the consequences? How big are the fires? How big are the gas releases that can occur if leaks or fires were to occur in this equipment? In addition to the consequence, you're going to want to be concerned with the likelihood at which these releases occur. So, for instance, leaks from sealing systems and compressors are going to occur at a much higher frequency than leaks in welded piping, which are very, very rare. So your risk analysis is going to need to be sensitive to that. Then we're also going to want to look at, well, things that drive the overall risk, but are outside of the actual loss of containment event. Things like what degree of occupancy is there in the zone that's under study? What are the probabilities of ignition if gas releases occur? And then also you might want to consider things that go beyond safety in your fire and gas system design, such as the production value of the process. There is value in providing fire and gas system protection simply to avoid large commercial losses and not just looking at the personnel safety attributes of fire and gas system design. Now, looking at all of those attributes and using some sort of risk modeling tool, you're going to want to select the performance targets for the zone. Specifically, what is the safety availability of the fire and gas loops, and what is the coverage of the fire and gas detector array. Now, there are two common approaches to selecting these targets. And these common approaches are semi-quantitative, order of magnitude type approaches that are similar to LOPA, where you're going to use tables and order of magnitude selections in various risk parameters to establish those performance requirements. And again, those semi-quantitative techniques are going to need to be calibrated to ensure that those rough and quick tools are going to provide satisfactory results. The other approach is to use a fully quantitative risk analysis to verify that your quantitative tolerable risk goals have been achieved for each zone. And while the quantitative risk analysis technique is going to provide much more accurate results, it is also extremely time-consuming and very expensive. So as a result, most organizations tend to want to use a semi-quantitative approach that has been calibrated using quantitative risk analysis techniques. Now, the performance targets that these techniques are going to establish, and whether you use a semi-quantitative approach or a fully quantitative approach, you're going to define the same types of performance targets. You're going to specify fire and gas detector coverage and equipment probability of failure. Now, if you're selecting, or if you're looking at fire and gas detector coverage, the ISA 84.00.07 technical report defines two types of coverage that you may wish to calculate. Those two coverage types are geographic coverage and scenario coverage. Geographic coverage is a type of coverage which essentially looks at a fire detector array or a gas detector array, and for that specific set of equipment and a given elevation of interest, will calculate what fraction of the floor space or what fraction of that elevation of interest can that detector array see. So if a fire were to occur in a specific location, would that detector array be able to see it? And that coverage is usually presented in terms of a color-coded map in addition to tabular results. The color-coded map might, for instance, have red where no detectors can see the fire, yellow where only one detector can see the fire, and green where two or more detectors can see the fire. That visual map will then also be supplemented with tables where the coverage is actually calculated in terms of percentages of the floor space that are either no coverage, one coverage, or two or more coverage. Most of the order of magnitude or semi-quantitative techniques for fire and gas system performance design utilize geographic coverage techniques. So for most project applications, the coverage is going to be specified in terms of geographic coverage, and geographic coverage techniques will be used to calculate for coverage calculation for verification purposes. The other type of detector coverage is scenario coverage. Now, you'll notice that in our discussions of geographic coverage techniques, we didn't discuss at all where the fires or where the gas releases are likely to occur. All we looked at is essentially what can the detector see, and we completely ignored where the fires are coming from. In reality, we haven't ignored where the fires are coming from. We will address that issue a little bit later, and specifically, that issue is going to be covered by setting coverage areas and extent of covered areas when we use the semi-quantitative techniques. But when we're calculating scenario coverage, that's what we're going to consider, not only where the detectors are placed, but also where are the risk scenarios occurring. Scenario coverage is what we're going to use when we perform a completely, fully quantitative fire and gas system analysis. For scenario coverage, we are literally going to calculate the magnitude and location of every gas release scenario and every fire scenario that could occur in a zone. And then for each one of those literally tens of thousands to hundreds of thousands of scenarios, we're going to determine one at a time for each scenario, is there one detector, two detectors, two or more detectors, or no detectors that can actually see that scenario. And the outcome of the scenario coverage will essentially be a map of where the risk scenarios are occurring, a geographic risk profile, for those of you that are familiar with quantitative risk analysis, and also a mitigated geographic risk profile where the scenarios that have been detected are removed from the geographic risk. And also, with respect to performing calculations, there will be a tabular calculation of the fraction of the scenarios that are not detected, the fraction of the scenarios that are detected by only one detector, and the fraction of the scenarios that are detected by two or more scenarios. In addition to calculating coverage or setting performance targets for coverage, we will also set targets for probability of failure on demand of the electrical equipment, the safety instrumented function, if you will. Now, the ISA 84.00.07 technical report specifically defines the metric that we're trying to achieve in terms of safety availability, because the writers of that standard believe that a safety availability metric is more appropriate than the SIL, specifically because very high SIL targets, such as SIL 3 and SIL 4, are nonsensical for fire and gas system design. And the reason is that the fire and gas coverage would need to be ridiculously high in order for the difference between a SIL 2 and a SIL 3 probability of failure to even be noticed in the overall risk. So more precision was required on the lower end of the SIL spectrum. So it was determined that safety availability would be a more appropriate target, where a lot of the semi-quantitative approaches would have SIL targets for different fire and gas functions being low SIL 1 to high SIL 1 as opposed to SIL 1, 2, or 3. Even achievement of a SIL 2 for a single fire and gas system loop is going to make the probability of failure component of the overall risk so imperceptibly low in relation to all of the other risk factors that trying to achieve even better performance for the probability of failure is essentially a waste of resources because it's insignificant in the overall scheme of the risk. Now, in order to fully understand the different approaches that are available for setting performance targets, it's best to start by understanding the fully quantitative approach. This is true not only for fire and gas system design, but safety instrumented system design and risk analysis in general. If you fully understand all of the attributes of a fully quantitative approach. It makes it more easy to look at a semi-quantitative approach and understand what shortcuts have been taken, what simplifications have been made, and understand why those simplifications are appropriate and will still result in a risk calculation that will result in an effective design, even though the amount of effort expended on the risk analysis is orders of magnitude smaller. So in order to understand the fully quantitative approach, we start by explaining that the fully quantitative approach is going to calculate the targets that are required from the fire and gas detection and suppression system using rigorous mathematical models to estimate the likelihood of an event and the consequences, the magnitude of the consequences if that event were to occur. The consequences are going to be characterized by source term modeling that will define what a release looks like if a loss of containment were to occur. Then that source term is analyzed using dispersion modeling to determine the extent of the clouds that will be generated and the location of those clouds once the material leaves the pipe and disperses throughout the plant. And then finally, fire models and explosion models will be used to determine what the effects on people and equipment are if those releases are ignited. And even if those releases are not ignited, if toxics are present, it will determine the magnitude of consequence to personnel that are exposed to toxic materials. The release likelihood is going to be calculated, but it's going to be calculated in a way that is drastically different than many people would expect, especially if they have a background in doing the simplified layer of protection analysis technique. With a fire and gas detection and suppression system, we do not assume that we are going to be able to know what the causes of loss of containment are. In fact, if a cause of loss of containment is well known and well understood, we would have expected that the process hazards analysis and the LOPA techniques would have adequately addressed the risks of those hazards using preventive techniques. Mitigative techniques, on the other hand, are to control those risks that are not well defined, not well understood, and cannot be well planned for ahead of time. And instead of trying to calculate how frequently a release will occur based on a set of known initiating events, we are going to instead do a statistical probabilistic technique that will infer the rates of loss of containment based on the quantity and type of equipment that is contained within a zone, and use historical analysis, statistics based on the history of these types of processing equipment to determine their leak rates, and also to statistically determine the distribution of the sizes of the leaks that have occurred. So we're not going to try to predict based on initiating events. Instead, we're going to look at statistically how often have leaks occurred in this type of processing equipment in the past, and use that as a basis for calculating how frequently we expect these leaks to occur in the future. After analyzing these figures, we'll look at the mitigating factors based on the site. And some of the mitigating factors will include ignition probabilities, again, based on the type of equipment that is being used and the ways that personnel interact with the equipment. The personnel interaction with the equipment will also define things like what is the frequency or the probability of human beings being exposed to these hazards, and also being able to respond to these hazards if they see them occurring or if they respond to personal monitors or general alarms. Then there are also other factors of the design of the facility, such as the spacing, the type of decking used, that is going to determine the consequences that can occur. Once all these factors are calculated, there will be an overall level of risk for that zone in the facility. That calculated risk will then be compared against the various tolerability criteria that are available from that organization. If the risk is tolerable, the as-is situation is acceptable, whether the as-is situation is existing fire and gas detection equipment or no fire and gas detection equipment. But if it is determined that the existing risk is not tolerable, some sort of design needs to be made. Some sort of recommendations for a fire and gas system design needs to be made to reduce the overall level of risk. Now, once the preliminary fire and gas system design has been put in place, all of those consequent scenarios and release scenarios that were defined are going to need to be considered using the scenario coverage technique and the calculation of safety availability to determine what is the beneficial effect that the fire and gas system has on achieving the overall tolerability of risk target. And the analysis will result in either a tolerable level of risk being achieved, or if the tolerable level of risk is not achieved, the fire and gas system design will need to be modified, trying to identify the weak points in the design, and then reanalyze in a recursive fashion until the tolerable risk levels have been achieved. Okay, the first step in the quantitative risk analysis technique is to identify the hazardous scenarios. The hazardous scenarios are going to include all of the general release and fire scenarios. And we're going to need to consider all of the credible scenarios and look at each piece of equipment that may suffer a loss of containment. These will include vessels, process piping, flanges, instruments, wellheads, pumps, compressors, heat exchangers, pig launchers, pig receivers, risers, and pipelines. After identifying all of the credible leak sources, we'll need to identify the specific factors that affect the release scenario or that define the magnitude of what we refer to as the source term in quantitative risk analysis. These include what is the hole size, what is the location of the equipment, what is the orientation of the release, what is the phase of the release? Is it a liquid? Is it a gas? Is it a two-phase release? And when the released material, when the material is released, will it pool, and will that pool have a secondary vaporization term? We're going to need to consider the toxicity of the material and then also the occupancy of the area where the material is being released. When performing this analysis, if some release scenarios are determined to have an extremely low likelihood or an extremely low consequence, sometimes these scenarios can be thrown out without further consideration, simplifying the analysis and decreasing the amount of time required to perform the analysis. The results of this task should be a detailed list of all of the release scenarios that are going to be required to be analyzed. And these scenarios are going to have enough detail so that a consequence analysis and a likelihood analysis can be undertaken. And for each one of the release scenarios, we're going to identify a list of the potential incident outcomes, such as jet fires, flash fires, vapor cloud fires, and pool fires. After the consequence analysis has been performed, a likelihood analysis will need to be performed. As mentioned previously, the likelihood analysis is not performed using predictive techniques that are based on knowledge of the scenario by which the loss of containment occurs. Instead, a statistical probabilistic inference technique is going to be used to estimate future release rates or loss of containment rates based on historical data of which these releases have occurred. Some of the databases that should be considered when performing the likelihood analysis include offshore release statistics from the UK Health and Safety Executive, and Parlock 2001 from the UK HSE. These are some of the openly available sources, but ultimately these analyses need to be specific to the facilities that are under study and specific to the various operating companies. So if leak statistic compilation and correlation techniques have not been implemented in an organization, they should be. So, and that will allow the use of a specific organization's leak rates to help in this task of determining the likelihood, which will make it more appropriate and more specific to the facility under study. Now, all of the information that is collected and all the information that's presented in the publicly available sources are going to be sensitive to whole size distributions. So for any type of equipment under study, you're going to want to consider what is the likelihood of very small leaks, medium leaks, large leaks, essentially pipe diameter, for instance, being the largest whole size leak that would be considered. In addition to the whole size distribution, it should be very specific to the equipment type. Seal failures on pumps occur much more frequently than vessel failures. So the leak rates must be specific on the type of equipment that is under study. Okay, once all of the equipment items are known, a likelihood analysis is going to proceed by either on a zone-by-zone basis or an equipment-by-equipment basis, where you will list all of the equipment in the zone, or for a specific equipment item, you will list it and all of its appurtenances, pipes, and connections. And then create the inventory of all of the equipment in that zone, for instance. And for each equipment item, you will need to list a rate for that equipment item type, and also for the specific type hole size that is under study. Then you will multiply the number of the equipment items by the leak rate to get a leak rate per equipment item type, and finally sum all of your leak rates together for an equipment item or a zone to give you an overall leak rate for the zone. That final likelihood number is then combined with the different consequence magnitudes to assess the overall risk. After the consequences and the likelihoods are known, a risk integration task is performed. The risk integration is where the consequence and likelihoods are joined together to generate a list of possible scenario outcomes. during the risk integration, each outcome is going to have an associated level of risk. And event trees are going to be used to analyze look at each incident outcome and then modify the risk posed by that incident outcome by the various mitigating factors such as ignition probabilities, probabilities of explosion, probabilities of occupancy, and mitigation effectiveness. Then each one of the event outcomes is going to be integrated using a risk integration tool for a fire and gas zone, or possibly overall for a platform or a facility. Okay, so for each scenario, there is going to be a frequency of occurrence, a consequence associated with occurrence in terms of probable loss of life or equipment damage, and then a zone size or a zone footprint for the hazard. Each one of those, and there will literally be hundreds of thousands, possibly millions per zone, will then need to be combined using a quantitative risk assessment tool. The outcome will be the calculation of the overall probable loss of life for the area under study, such as the zone, and it will also include such factors as the geographic risk profile, unmitigated with the fire and gas system, the geographic risk profile mitigated with the fire and gas system, the scenario coverage, and the safety availability of the system, all in a tabular format presented to determine whether or not the coverage targets have been achieved. Initially, this process is done by selecting a low detector coverage and then progressively increasing the amount of detectors and the safety availability of the safety instrumented system until the tolerable risk target has been achieved. This is going to occur in a recursive fashion. Now, understanding how the risk integration works and how detector coverage and how fire and gas system effectiveness is incorporated into the overall risk analysis, what needs to be done is to consider the detector coverage and the fire and gas system effectiveness, as is shown in the risk integration event tree shown below. Initially, there will be a loss of containment event or release that is going to have a certain frequency associated with it. Then you will consider the other mitigating factors, in this case, probability of early ignition, probability of delayed ignition, residual fire detection, and residual fire and gas system effectiveness. The two items that are highlighted in yellow on this figure are the detector coverage and the effectiveness of the fire and gas system. So in this case, we calculated an 85% coverage, scenario coverage, and a 90% probability of failure on demand, or safety availability effectiveness for the fire and gas detection and suppression system. Using those figures of 85% scenario coverage and 90% fire and gas system effectiveness, we then calculate the frequency of each branch along with the associated consequence of each branch. And then all of the branch frequencies that result in a hazardous consequence are summed together to calculate an overall frequency. That overall frequency then is compared against the tolerable risk target. If the risk target is achieved, the design is adequate and you move to the next zone. If the tolerability of target tolerability risk target was not achieved, then the detector coverage and probability of failure on demand will need to be increased by manipulating the design of the fire and gas system and the number and placement of the detectors until the performance target is achieved. Okay, now that the fully quantitative approach has been discussed, the semi-quantitative approach will be discussed, and specifically how it differs from the fully quantitative approach and why most practitioners feel that this approach is much more effective, much less time consuming, while providing equally accurate results based on calibration of the parameters and tools that are used to perform the semi-quantitative approach. Calibration using the fully quantitative risk analysis technique. In a semi-quantitative approach, you're going to use a team-based analysis of the risk that a zone poses using calibrated risk assessment tables. And those tables are going to consider the factors that will drive the risk associated with a given zone. The risk factors that are going to be qualitatively ranked by the team performing the semi-quantitative study include the likelihood of releases based on the type of equipment, the consequence of loss of containment scenarios in the zone, and what are the mitigating factors that will either decrease the risk or increase the risk given that a loss of containment event has occurred in the zone. Once the categories have been selected for each of those attributes based on the team, those selected categories will be used inside of a risk graph or a risk matrix tool to determine the zone grade. And the zone grade is going to be, each zone grade will have performance targets assigned to it that will make the risk tolerable for that category of risk. For instance, a typical set of zone grades might go A through C, with A representing a very high risk and C representing a low risk, where the high risk might require 90% geographic coverage and 95% safety availability, but the low risk grade C might only require 60% geographic coverage and 90% safety availability to achieve tolerable risk goals. The primary factor that is going to determine whether or not a semi-quantitative approach is going to ensure that tolerable risk levels are achieved is a detailed and comprehensive calibration of the tables and the performance targets that are used in the semi-quantitative approach to ensure that when a grade C is selected, the associated safety availability and coverage targets will allow tolerable risk to achieve. This calibration process is typically going to be performed by doing a full QRA of some typical process zones that have been given typical performance targets or zone grades. It's also important to note that the calibration technique is typically going to be based on a geographic coverage as opposed to a scenario coverage, because what has been determined by experts in the field through numerous full QRA calibrations is that geographic coverage for a well-defined zone is going to correlate very well to scenario coverage, which then correlates very well to overall risk. And since calculation of geographic coverage is significantly easier to perform than scenario coverage, most organizations' performance-based fire and gas philosophies dictate the use of geographic coverage as opposed to full scenario coverage. Now, how geographic coverage is going to provide adequate results in comparison to scenario coverage is to ensure that the graded areas only extend as far as the hazards occur. When performing a grading, not only are you going to set a category A, B, or C for what are the performance targets, you also want to define the extent of that graded area so that they only encompass the area surrounding the leak sources. The technique for defining the extent of graded areas is going to be very similar to how you would define for how you would perform electrical area classification. What you need to do is identify where leak sources are, and then for each of those leak sources, you're going to set a distance away from the leak source that you want to be considered inside the classified area. And then in some cases, you might want to define a secondary lower grade for all areas adjacent to a high-risk grade. So in the drawing below, the grade A areas might be represented by red, and you might want to have a certain grade B or yellow area surrounding a grade A area to ensure that the risk is appropriately addressed. And then also, similarly for grade B, and then other lower grades may not require additional standoff areas. So the philosophy document that an organization generates is going to need to define not only how areas are graded, but also what are the extents of the graded areas geographically in relation to the leak sources that are present. Then when a geographic coverage is performed, you only calculate the coverage of the graded area, not the entire zone. This will prevent you from analyzing areas where there is no risk, because those areas would be ungraded, or in the drawing below, they would be white. The next step after selecting the performance targets is the actual verification of the fire and gas system detector coverage. The fire and gas system detector coverage is going to be based on the definition of the zones, the performance targets for those zones, and the philosophy and procedures for performing a coverage calculation. We highly recommend performing verification of detector coverage using the FGS Fire and Gas Detection and Suppression System Fire and Gas Mapping software tool. The result of this analysis will be a visual fire and gas map that will give you a color-coded definition of which areas are covered and the degree to which they are covered, along with tabular information that defines the calculated fractions of the covered areas of the different types. The new feature that's included in the ISA 84.00.07 technical report that is not included in the ISA 84 or the IEC 61511 standard is the addition of coverage as a performance metric that must be achieved in addition to the safety availability, which again is related to the safety integrity level or SIL of a safety instrumented function. One might ask, why is verifying detector coverage important? Why is it important? Why can't we just, instead of verifying detector coverage and specifying it, just use safety integrity level alone as the metric, the single metric that safety, the basis of safety is based on? And the reason that detector coverage is important is that the failing of most fire and gas detection and prevention systems is not related to a failure of the electrical equipment itself. Instead, it's the failure of a device to be located in a location where it will be able to detect a gas release or a fire. So the failure of a fire and gas system, as opposed to safety instrumented system, is going to be related to one of two mechanisms. Either it can be related to inadequate coverage, meaning that there aren't enough detectors and those detectors aren't in the right locations. There isn't adequate numbers to provide the voting that is desired. That would be an example of inadequate coverage, which is the primary factor governing the probability of failure of a fire and gas detection and suppression system. In addition, there is inadequate availability, which means a hardware component failed to function as intended, and as a result, the fire and gas system did not activate. What we need to do to ensure that one can think of high safety integrity levels in a fire and gas detection and suppression system the same way as the Maginot Line during World War II. At the outset of World War II, the French were concerned that Germany might invade. And as a result, they built up a lot of fortifications along the border between Germany and France. And these fortifications were extremely strong. They were dug in, they were built of thick concrete bunkers, and they were spaced fairly close together, such that the Maginot Line formed a very good defense against a German ground attack directly against the line. This would be the equivalent of specifying SIL-3 functionality. The problem with the Maginot Line is the same as the problem of a SIL-3 fire and gas detection and suppression system. Ultimately, France did not have an integrity problem. The fortifications were very strong, and they would have absolutely effectively withstood an attack. The problem that they had instead was a coverage problem. So seeing the forces all concentrated along the line between France and Germany, the German invasion simply walked around the line and went up through Belgium, through the forests, and came through the north of France, and also the Luftwaffe simply flew over top of the line. So again, they focused all of their resources on a very high integrity system and ignored coverage. And that ultimately is what led to the failure of the Maginot Line. And ignoring coverage is what will also lead to the failure of a high integrity fire and gas detection and suppression system where coverage is ignored. So in order to ensure that the detector layout coverage is adequate, it will need to be assessed. What you need to do is you need to ensure that the footprint of the coverage, meaning the area at a certain level of elevation that the fire and gas detection array can see,
is adequate to provide the required alarms and control actions for the given scenarios in that zone. Also, it's important to ensure that the detector views are not impeded by pipework, cable trays, or other obstructions. Those obstructions need to be considered in 3 dimensions when the coverage analysis is being performed. Overall, with respect to detector coverage and probability of failure on demand, an important statistic was generated by the UK Health and Safety Executive, HSE. What they determined was that 40% of major gas releases in the North Sea, these are not pinhole leaks or small transients, but these are major gas releases. 40% of these major gas releases were not detected by the fixed gas detection systems that were in place. Again, this strongly indicates that you have a coverage problem with existing gas and fire detection systems as opposed to an integrity problem. Now, there are 2 methods that are defined in the ISA technical report from Working Group 7 that defines the methods and practices for fire and gas, performance-based fire and gas detection and suppression systems. The 2 types of coverage are geographic coverage and scenario coverage. Geographic coverage is the fraction of the geometric area at a given elevation of analysis of a defined monitored process area that, if a release were to occur in a given geographic location, would be detected by the release detection equipment considering the defined voting arrangement. The other type of coverage is called scenario coverage. Detector scenario coverage is the fraction of release scenarios that would occur as a result of the loss of containment from items of equipment of a defined and monitored process area that can be detected by release detection equipment considering the frequency and the magnitude of the release scenarios and the defined voting arrangement. So these are the 2 types of coverages that are defined in the technical report, and both of these have their place depending on whether you would be using more quantitative risk analysis techniques to analyze your risk or more qualitative. The more qualitative procedures typically default to geographic coverage as it is more easily calculated and yet very powerful in specifications and design. And the scenario coverage is more rigorous, but also much more time-consuming to generate. And that is the type of coverage that would be required when considering an analysis in a more quantitative fashion. When performing a fire and gas detector mapping assessment, one needs to consider many attributes of the zone in consideration. The first consideration would be the performance of the detector. The performance of the detector is generally calculated, determined, measured by the equipment vendors that are providing the detectors. In the picture to the right, you can see that a fire and gas detection and an optical fire detector vendor provided what is called a cone of vision drawing for their detector at 3 different sensitivity settings, high, low, and medium, or high, medium, and low. And when performing a fire and gas detection map, the software tool or any tool or procedure that you use to perform modeling will need to faithfully reproduce the cone of vision of that specific equipment vendor, as different vendors will provide different cones of vision and have different performance characteristics. One can't simply use a generic model and apply it to all detectors. Different detectors have different attributes and different performance levels at different settings. It's important to remember, though, that the cone of vision that is drawn in the literature from an equipment vendor is only valid under a certain specific set of conditions. Specifically, in order for the cone of vision to precisely match what is supplied by the equipment vendor, the only time that would be true is if the detector that is being analyzed is exactly at the elevation of interest. So the detector and the elevation of interest are identical. Furthermore, the detector has to be aimed, has to be oriented so that its line of sight is completely parallel with the plane of the elevation of interest. And only under that narrow set of circumstances will the coverage map exactly match the cone of vision that's provided by the equipment vendor. As the detector is elevated away from the elevation of interest and the angle of declination increases, or the detector is pointed down towards the floor, the shape of the cone of vision dramatically changes. No longer do you get a sharp 45-degree angle cone of vision, and instead you get something that ends up looking a little bit more elliptical until the angle of declination is such that the detector is pointed straight down, at which point in time, depending on the make and model of the optical fire detector, you will have a circular cone of vision. Okay, so the detector coverage is going to be calculated based on three-dimensional modeling. Essentially, analytical geometry is going to be used. The cone of vision is essentially a cone, and the intersection of a cone with a plane is the realm of conic sections. So the conic sections that are generated when a plane intersects a cone can be used to generate the footprint, if you will, of the cone of vision on the elevation of interest. And this needs to be done fully in 3 dimensions. So, and also as you are performing analyses and looking at software tools that will generate cones of vision, it's important to ensure that the achieved coverage target is compared against the performance target that was provided or that was calculated based on the zone categorization to ensure that the performance targets are met. And this analysis needs to not only consider the footprint of the cone of vision of the optical fire detector at the elevation of interest, it also needs to consider the effects of shadows that are cast by objects that are in the path of the fire detector. So any obstruction between the fire detector and the elevation of interest will cast a shadow on the elevation of interest, which then needs to be essentially removed from the coverage map. Ultimately, the fire and gas mapping output should look like the figures shown on this slide. In the top left corner, you can see geographic fire detector coverage. In this specific output, areas that are shown in green are covered by 2 or more detectors. Areas that are covered in yellow are only detected by a single detector, and areas that are shown in red are seen by no detectors. So there is no coverage at that location in the elevation of interest. Other items that you might want to note are areas that are grayed out would be areas where there is equipment located on the elevation of interest. Thus, that needs to be removed from the calculation of coverage, as it is inside the vessel, thus does not need to be covered inside the vessel or the piece of equipment. Below that, you'll see a geographic gas detector coverage, which looks substantially similar in that the color scheme, again, is dependent on the number of detectors that can see a particular location. The left-hand side of the graph shows geographic coverages. The right-hand side shows scenario-based coverage. And what you're looking at here is not what areas are covered and what areas are not covered, but instead you're looking at a geographic risk profile. So essentially, the color at any particular location is indicative of the frequency at which a gas release or a fire scenario will exist at that given location. The hotter the color, the more likely that a release will exist at that location. So in the top picture on the geographic risk section, you'll see that close to the meter in this metering skid that has been modeled, as you get closer to the meter, the risk is elevated, which makes sense. As you get further away from the meter, the risk begins to drop off. Now, this risk on the top is unmitigated. It simply looks at the leak sources, the dispersion modeling of a leak, and the frequency at which those leaks are supposed to occur or are expected to occur. In the lower drawing, what you see is a modified geographic risk profile. And in the modified geographic risk profile, what occurs is that if a release scenario is detected by the detection array, it will be removed from the analysis, removed from the calculation of geographic risk. If you look at the drawing, you'll see that the detection array that was chosen for this metering skid was 2 open path detectors, one on either side of the metering skid. And you'll further see that the risk has been substantially decreased, whereas on the top unmitigated drawing, you'll see a lot of yellow, quite a bit of green. On the bottom, you'll see that there's no yellow, a more limited amount of green, and more of the cooler colors. Also, you'll see that a lot of the area has no geographic risk essentially associated with it, because any releases that would occur in that direction would be detected by the fire and gas detection and suppression system. Ultimately, the scenario-based coverage is going to calculate a fraction of the number of release scenarios that are detected by the fire or gas detection array. After looking at coverage, the next step is to verify the availability of the fire and gas detection and suppression system. This safety availability calculation is very similar to the SIL calculations. In fact, it's identical to the SIL calculations that are performed for safety instrumented systems. When you define a fire and gas function, an FGS function, you begin with a conceptual design that the designers believe will achieve the specified safety availability target. What you're doing during the conceptual design stage is selecting equipment that is appropriate for the performance target, and then specifying how the system operates in both specific details for each individual loop, and then also general requirements that apply to an overall system. The result of this conceptual design task is going to be an FGS requirement specification that defines all of the FGS functions. Now, each of those FGS functions are going to be required to achieve a safety availability target. And there are multiple parameters that affect a function's ability to achieve its safety availability target. Those attributes include component selection, fault tolerance, functional test interval, the effect of common cause failures, the diagnostic coverage of the devices in the loop. All of these items are factored into the calculations that verify whether or not an appropriate safety availability has been achieved. The actual verification is done typically by using some sort of probability of failure on demand modeling tool. The excerpt that is shown here is from the Kenexis FGS Design Basis Toolkit, whose calculations are primarily based on the simplified equations that are contained in ISA Technical Report 84.00.02, which is the premier source of calculation equations for performing safety availability and probability of failure on demand calculations. If, as an option, calculations can be performed manually using the same equations that are in that technical report, and calculations can also be performed inside other tools such as fault tree analysis or by using Markov models. But the great preponderance of practitioners of performance-based design do use the equations that are at least derived from what is presented in the ISA 84.00.02 technical report. After all of the loops have been verified to achieve their safety availability target, the final design needs to be documented in an FGS requirement specification, or it's sometimes called an FGS safety requirement specification. The FGS requirement specification defines how the fire and gas detection and suppression system will perform, and it is essentially a design specification that is the basis for the supply and the engineering of the FGS equipment. The FGS requirement specification is going to contain two types of specifications. The functional specifications that define what the system is required to do and how it will do it, but it also contains integrity specifications, which basically define how well the system is to perform its task. And those integrity specifications are essentially the safety availability targets of the functions along with the coverage targets of the functions. Good instrumentation and control design dictates that an FGS requirement specification is typically not a single document. Many poor requirement specifications have been developed that are essentially what could be considered a safety case. Practitioners that are not familiar with instrumentation and control design, but are very familiar with how the standards, i.e. the IEC 61511 or the ISA 84 standard are written, will know that the IEC 61511 contains a section that has a list of all of the line items, all of the bullet items that define the things that a FGS requirement specification should include. And unfortunately, many of these people make an attempt to document the design of their system in the same format that the standard presents the requirements, which is actually a bad way to present a design. It ignores the user of the specification, who is not an assessor that is verifying that the standards have been met. And furthermore, it results in poor practices of duplication of multiple pieces of information in multiple locations without providing any benefit for doing so, which opens up a lot of problems over the life cycle of the facility, as a lot of the information that is presented starts to mismatch in the multiple locations in which it's presented. Optimal specification design will use multiple documents and also use referrals to other documents where some of the information that's required to be specified may exist already and does not need to be repeated. Okay, so two of the main documents that will comprise a FGS requirement specification, or typically this is going to fall into the logic solver functional specification, would be, number one, the logic description. And far and away the most common method for documenting logic in a fire and gas detection and suppression system is a cause and effect diagram. But in some cases, binary logic diagrams are used, or even other methods such as narratives or simple text. In addition to the logic diagrams, the cause and effect diagrams, you may also need general notes. First off, there's going to be general requirements that apply to all of the functionality in a fire and gas system, which is much more efficient to list that information once, and then in the detailed sections only list exceptions to the general rules. And then also there will be often requirements for general notes where there are special considerations, or the logic is too complex to simply be represented by an X in a cause and effect diagram. These are good situations to provide general notes which clarify and supplement the logic diagram. Okay, this slide shows you a typical example of what we would expect in a cause and effect diagram, with inputs on the rows and effects on the columns. And in addition to the tag names, other information including engineering units, trip points, delays, whether or not the inputs and outputs are safety critical, drawing numbers that the instrumentation is included on. These are all common attributes of cause and effect diagrams for logic description. General requirements and detailed notes, as mentioned previously, are plain text and typically are simply listed in a numerical fashion in a word processing document. After the conceptual design phase and after the verification of the safety availability of all of the FGS functions, the next step is to perform the detailed design and detailed specification of the FGS system. This step is not dramatically different from what has traditionally been done for fire and gas detection and suppression systems and for instrumentation and control systems in general. This would include the development of loop sheets, preparation of internal wiring diagrams, drawing of cable schedules, and also the development of PLC programs where programmable systems are used as the logic solvers for the FGS. After the detailed design is complete, or sometimes in parallel with the detailed design, is the development of procedures by which the FGS system will be used. There are multiple procedures that need to be developed at this phase and considered prior to more time-critical steps in the life cycle, such as startup and operational phase. The development of these procedures is an important task because it allows the design team to be able to think through how the FGS system is going to be interacted with. Procedures that need to be developed include operation of the FGS, what needs to be done to start the system up, what needs to be done to reset the system after it has been activated, and under what circumstances will the system need to be bypassed and how will those bypasses be performed. During the development of these procedures, sometimes shortcomings in the design are evidenced, and the procedure development requires revisiting earlier phases in the safety life cycle to include new equipment to allow things like bypasses and resets to be performed while the system is online and functioning. Also, maintenance procedures for the system need to be developed. Importantly, the response to detected failures needs to be developed and considered. If a component in an FGS system fails, it's important that that component, the failure be detected quickly and the failure be repaired within the mean time to failure that was assumed during the design phase and was used as an assumption in the safety availability calculation. If the repair is not done within that time frame, the achieved safety availability and the overall tolerable risk levels of the facility might be violated by not repairing that device as scheduled and as assumed. So in order to ensure that all the potential repairs can be done, developing the procedures is important, as it will yield requirements for spare parts, staffing, and diagnostics enunciation and cooperation between the maintenance staff and the operations staff. Also, on a periodic basis, the FGS system is going to need to be maintained and is going to need to be tested. And development of those procedures needs to be performed, again, prior to the final design of the system, so that if required, the final design can be modified to meet any unforeseen situations that are created as a result of maintenance and testing requirements. After procedure development and after the detailed design has been performed, the system is built and it is installed and commissioned on site. This task, again, is very similar to traditional fire and gas system design and instrumentation and control system design in general. This task involves the purchasing of the equipment, the construction of the cabinets and assembly of the equipment into cabinets, then the installation of the cabinets and the field equipment and all the interconnecting wiring on site. Installation of the field equipment for fire and gas detection and suppression systems is also going to be very important, because the location and the orientation of the detector array have a very strong impact on the ability to achieve your tolerable risk targets. Thus, it is not enough to simply confirm that the device is in the field somewhere. It needs to be in the specific location that was specified. It needs to be at the specific orientation, meaning angle of rotation and angle of declination that was specified. Furthermore, you'll need to confirm the field of view of the detectors is consistent with what was assumed during the design phase. And if not, the coverage models need to be recalculated to confirm that coverage targets have still been achieved. After the installation, the software needs to be loaded onto the system. The wiring needs to be connected, and all of the loops need to be commissioned to ensure that the instruments are operational and correctly communicating with the FGS logic solver. After the commissioning phase is complete and the instrumentation and control constructors are ready to turn the system over to the operating company for operations, a pre-startup acceptance test, or in the terminology of the IEC 61511 standard, a validation needs to be performed. During this task, we're going to verify that all of the installed equipment and all of the software conform not to the detailed design documents, but to the FGS requirement specification or the safety requirement specification. This is to ensure that errors were not generated in the detailed design documents, and if they were, they can be caught prior to the startup. All of the software and the hardware needs to be reviewed one more time to ensure that everything matches the safety requirement specification and is operational. And then all of the loops need to be tested. So the PSAT, or the validation, involves a full physical test from the field back to the control room and back out to the field for any safety critical actions that the FGS system will take. If any deviations from the FGS requirement specification are noted, they need to be documented in a deviation record, usually called a punch list, and then all of the items on the deviation record need to be satisfactorily resolved before the system can be put in operation in a safety critical application. After pre-startup acceptance testing, you're off to the normal operation and maintenance phase. During the operation and maintenance phase, you will need to perform periodic function testing and maintenance to maintain the FGS at its safety availability target and at its performance detector coverage target. You'll also need to respond to overt faults in the system with corrective maintenance tasks. And other than that, hopefully, nothing will happen. The best situation is to invest in a good, well-designed fire and gas system and have it never activate. But you will know that if it's necessary, if fires occur, if gas releases occur, that system will be available to take the mitigative actions that it's been designed to perform. Management of change occurs when any modification to the facility occurs. This is more comprehensive than simply looking at changes to the fire and gas system hardware itself. Things as seemingly benign as adding stairs, moving a ladder, adding a piece of process equipment change the effectiveness of the fire and gas detection and suppression system. Adding new equipment may increase the number of leak sources, changing the definition of the zones, possibly changing the categorization of the zones. And at a minimum, these additional pieces of equipment create new obstructions that change the coverage that's achieved by the fire and gas detection arrays. So the scope of changes that will affect the fire and gas detection system's ability to achieve the tolerability of risk targets of an organization are affected by a wide range of materials. As a result, you're going to want to make sure that your existing management of change procedures for the facility include steps for review of all changes to determine if the fire and gas system is impacted by those changes. And if it is, the appropriate level of redesign and return to the appropriate steps in the safety life cycle of the fire and gas detection and suppression system are initiated by those changes. But again, it's also important to remember that a new or separate management of change system that's dedicated to the fire and gas system or to safety instrumentation in general is not appropriate. It is important to have one single unified management of change system that applies to all process changes, and making sure that that system adequately addresses the needs of fire and gas detection and suppression equipment.